In the previous lecture, we saw that adversaries can cause models to make egregious mistakes. Another source of hazards is the system or context in which a model is embedded. That can give rise to black swan and long tail events, which can also be extremely impactful and cause models to make severe mistakes as well. How can we understand or improve the robustness of models in the face of black swan or long tail or unexpected events? Well, the first step is through measurement. If we can't measure it, it's very difficult to know whether we're making progress or whether we're capturing any relevant phenomena. So what we can do is we could simulate extreme or highly unusual events using stress test datasets. These stress test datasets are derived from a different data generating process than the data generating process that produced the training data. For a simple example, consider the ImageNet dataset. People went around with their cameras taking pictures and uploading them to Flickr. However, if somebody took lots of pictures in an obscure location or, say, underwater, that would tend to come from a different data generating process than the usual images you would find on ImageNet. If an agent is trained to solve typical tasks, but then we put it in a simulated environment with lots of futuristic science fiction scenarios, that would be a different data generating process, and that would be testing its robustness to extreme or highly unusual events. The goal of doing this measurement is to make sure that the model performance does not degrade as sharply in the face of extreme stressors. If we can do that, that will greatly help improve robustness to these unusual events. We'll now look at many examples of stress test datasets in vision and natural language processing. We'll start with one of the earliest datasets, a vision dataset called ImageNet-C. ImageNet-C has many different corruptions. It's got 15 different corruptions, and each corruption is at 5 severity levels. So there might be a slight amount of Gaussian noise all the way to a very extreme amount of Gaussian noise. ImageNet-C spans different noise types, different blur types, different weather corruptions, and different digital corruptions too. The object is to train ImageNet models on clean images and then test the generalization of models on these corrupted examples. So if we do that for a ResNet 50 model, it gets 76% accuracy on clean ImageNet. And if we test on these corruptions, and it's never seen these corruptions before, then its accuracy is substantially less. For example, on snow, the accuracy is only 29%. Consequently, corruptions can pose a challenge to models and demonstrates that model performance can greatly degrade in the face of unexpected situations. Another stress test dataset is ImageNet-R, which tests robustness to rendition styles. The idea here is to train on the original ImageNet dataset and then test the model on ImageNet-R, which has different renditions such as art, cartoons, graffiti, embroidery, graphics, origami, paintings, patterns, plastic objects, plush objects, sculptures, line drawings, tattoos, toys, video games. So the models haven't seen these renditions before, but we're expecting them to generalize to them. This is a fair thing to ask because even some primate species have demonstrated the ability to recognize shape through line drawings despite not having seen those line drawings rendition styles before. So strong vision systems can generalize to changes in renditions. But the current computer vision models don't have this ability. To see how this comes from a different data generating process than the ImageNet dataset, we note that the ImageNet organizers instructed the annotators to avoid renditions. They said, no paintings or drawings. So this constitutes an actual distribution shift from the ImageNet dataset. I should note that this isn't a claim that renditions are intrinsically hard to recognize. If a person trains their model on renditions, they can definitely generalize to ImageNet-R. The only way that ImageNet-R becomes interesting is if people don't train on renditions. Renditions are a stressor with respect to the typical ImageNet dataset. Renditions are not a stressor with respect to the set of all images. So when we're testing robustness, we need to make sure that we're not training accidentally on renditions. Otherwise, we're not actually testing its ability to cope in the face of highly unusual situations. Currently, the performance on ImageNet-R for ResNet is about a 50% drop, but with more current computer vision models, the accuracy between the typical ImageNet accuracy and the ImageNet-R accuracy is about a 30% drop. Another way to create a stress test dataset is by mining for difficult examples through a process called adversarial filtration. The idea is to collect examples that fool an existing strong model and coming up with natural adversarial examples for that model. So one can mine for these hard examples or natural adversarial examples by having a model classify a large set of examples and create a test set of the examples that it got wrong. This is different from the adversarial examples in the previous lecture, which is more about modifying an already existing image. This is more about using real images and not modifying them, but just finding real images that pose especially large difficulties for models. Researchers can, in the process of adversarial filtration, collect egregious errors where models are highly mistaken, such as when they create high confidence misclassifications. So we might just not search for examples that models got wrong, but examples that models got extremely wrong. A dataset constructed through adversarial filtration is ImageNet-A. It contains naturally occurring examples, and they were collected based on whether a resonant 50 got them incorrect. So a resonant 50 model processed a large dataset of images, and the examples for which there were the resonant 50 gave an egregious misclassification were selected. We can see some of those examples below. I should note that these examples are not in any way adversarially perturbed. These are just examples that are naturally occurring but cause the model to make severe mistakes. There's no gradient noise applied to them. What we can see then is that adversarial filtration is a powerful technique that can help us find model failure modes and zoom into the error distribution. It turns out that the error distribution is remarkably consistent across models. So even though these were collected to fool a resonant 50 model, they actually transfer to various other models, such as vision transformers, which have completely different architectures, and those models also suffer in the face of natural adversarial examples. This demonstrates shared weaknesses across architectures. Another stress test dataset that is adversarial by nature is ObjectNet. Its examples are collected to show objects from new viewpoints on new backgrounds. For example, here's a chair rotated at an unusual angle. In a sense, there's an adversarial photographer, which are trying to take images of objects in unusual situations and make the familiar unfamiliar. Consequently, ObjectNet is another type of adversarial dataset. Now let's turn to a text dataset that is adversarially constructed. ANLI is an adversarial natural language inference dataset. Let's back up a bit. What is NLI? NLI is about determining whether a hypothesis is true, false, or underdetermined given a context. So there's some contextual information, and then we have a hypothesis potentially related to that context, and we're to determine whether the hypothesis is true, false, or underdetermined. That's what NLI is about, or natural language inference. The ANLI dataset is constructed by crowd workers with the aim of fooling large-scale models. So, for example, GPT-3 only gets up to 40% accuracy. Here's the ANLI construction process. First, an annotator writes a hypothesis. Then, a model makes a prediction about the context hypothesis pair. If the model's prediction was correct, the annotator writes a new hypothesis because the example didn't fool the model. If the model was fooled, the context hypothesis pair is validated by other annotators. So let's look at the schematic below. First, a writer creates a hypothesis. Then, that example is fed into a network. The network makes the prediction, and then there's a comparison. If the model got it correct, the example might go into the training set. If the model got it wrong, we're going to have somebody verify whether the model actually got it wrong. If the model actually got it correct, then the model would be discarded. If the model actually did get it wrong by way of this double checking, then the example will be added to either the train set, the dev set, or the test set. And then, as we can see in step 4, the model might be continually retrained as this data set is being constructed, so that the examples keep getting harder and harder, or that the writers need to come up with harder examples as the data set is being created. Now let's look at ways to improve long-tail robustness. It's the case that models with more parameters exhibit more robustness. On the left, we can see performance on ImageNet-C. MCE means mean corruption error, which is basically the ImageNet-C error, so lower is better. As the models get larger, we can see that the robustness increases. Likewise, on ImageNet-R at the right, we can see that the larger version of the model has a lower error. So even though the clean accuracy difference of that resnext between this baseline model and the larger model differs by less than 1%, the ImageNet error differs by a substantially larger percent between the two models. So there are outsized returns to having larger models. It's not just the case that the larger models are resulting in higher accuracy on the clean data set, and that's sort of driving an improvement on these unusual situations. Instead, there are distinct returns to robustness from using larger models. One possible intuition for this is that larger models have more parameters, so there's potentially more redundancy in the representations. So consequently, if one neuron fails, another neuron can potentially pick up the slack and detect the feature that should have been detected by the other neuron. If there are more neurons or more parameters in the network, then there's more of a possibility of higher redundancy. So that's one intuition for how larger models could exhibit more robustness. Some data augmentation techniques can improve robustness. One example is Mixup. Mixup augments the data by performing an element-wise convex combination on the inputs and outputs. Recall that a convex combination is this sort of weighted average where the sum of the weights is 1 and each weight is non-negative. So if we had two images, x sub I and x sub j, and there are two labels, then we would have this mix-up image. If we randomly sample the mix-up parameter to be 0.7, then we're having 70% cat, 30% dog. So the label is that the model must predict 70% confidence on cat and 30% confidence on dog. The algorithm is here as follows. We can see that lambda is sampled from a beta distribution. If alpha in that beta distribution is equal to 1, then we're just sampling from a uniform distribution. We can see the convex combination of the inputs and the convex combination of the labels. It's the case that mix-up improves corruption robustness. Not that dramatically, but it is an improvement over many other techniques. And for an intuition for mix-up, instead of images, which is a little less intuitive, you could imagine x sub I and x sub j being audio signals. Then if you just mix those audio signals together, mix-up is just mixing the audio in some sense. Another data augmentation technique that improves robustness is AutoAugment. AutoAugment proposes data augmentation strategies using Python imaging library augmentations such as invert, solarize, rotate, translate, and so on. AutoAugment composes two augmentations together, and each augmentation has two parameters. One parameter is the probability of the augmentation being activated or used or turned on, and the second parameter is the augmentation's intensity. At the right are some examples. We can see in the first column that some of the examples are rotated. There is an 80% probability of rotation, and the intensity of the rotation when it was on was 8. It was also combined with an equalize operation, which was less likely to be turned on at 40% probability, with an intensity of 4. To create these parameters for augmentation and these combinations, they trained tens of thousands of deep networks to search for a few augmentation parameters. and they proposed some of their best parameter settings. So consequently, finding these augmentations through AutoAugment was pretty computationally expensive. Rather than heavily optimizing an augmentation's parameters as AutoAugment does, perhaps we could rely on stochasticity to provide robustness. To avoid AutoAugment's computational cost, we may want to use randomized augmentations. These could allow us to achieve very diverse augmentations. But the typical way of creating a randomized augmentation and having a lot of variation would be to stack lots of sources of randomness together. But if we do this, we could have images that end up looking very distorted. So if we keep adding lots of different augmentation operations on top of each other, the resulting image is almost unrecognizable. So uncontrolled random augmentations is not a good idea. We'll need to come up with some other way to exploit lots of randomness to make it substantially more competitive for robustness compared to AutoAugment. One way to exploit the variation from random augmentations and avoid the computational costs associated with AutoAugment is AugMix. It uses random augmentations and mixes these augmentations together to keep the image recognizable. Let's look at a concrete example of AugMix. Continuing with the tortoise example, AugMix in the first step augments the image in 3 different ways. It randomly samples 3 different augmentation operations and applies those augmentations at a random intensity. Then, in the next step, AugMix potentially continues to augment the images in these branches. So, in this case, the first and third branch were continued to be augmented. These shear and equalize operators were randomly sampled from a larger pool of operations. Then, augmentation continues, in this case with posterize for the third branch, and the first branch didn't continue to be augmented. Then these different augmentations are mixed together through a random convex combination. And then finally, there's a skip connection where that augmented image is mixed in with the original image, and that results in the AugMix image. As we can see, we randomly sampled operations, the intensity, the depth of each branch, and all of the mixing weights. So AugMix incorporates various sources of uncertainty and stochasticity. But the result is an image that looks not too dissimilar from the original image. So the data generating process has a lot of different steps in it, which provides some underlying variety for the model to learn from. But it still doesn't distort the image, fortunately. So this is how combining multiple images can exploit various sources of stochasticity without resulting in a completely different image. As a technical detail, AugMix is applied on top of the typical data augmentation steps. Those steps might be flipping the image, cropping the image, or resizing it. So after it's gone through the typical data augmentation, then AugMix applies its augmentations on top of that. Here's the AugMix pseudocode. As we can see, the set of augmentations is rotate, translate, shear, etc. It's important not to have your augmentations leak if you're trying to test distribution shift robustness. Just as if you end up leaking images that follow the test distribution, if you end up leaking augmentations that look similar to the corruptions, that can be a problem too. So here are the ImageNet-C corruptions, and here are the pill operators used by AugMix. AugMix isn't using all of the pill operators. Some of the pill operators end up looking like the ImageNet-C corruptions. But for these corruptions at the right, these are fairly distinct from the ImageNet-C corruptions. So consequently, we're not just training on the distribution we're trying to test on. The final data augmentation method we'll consider in this lecture is PixMix. PixMix mixes training images with images from another dataset. So for example, we may have a mixing set which has lots of fractals. A typical bird training image, for instance, is mixed with an image from the fractal dataset. Or it's potentially mixed in with an augmented version of the image. So in the example below, we can see the bird is being mixed with the mixing set image, in this case some fractal. And then in the next step, it's being mixed in with a posterized version of the original training image. And then it's being mixed in again with that same mixing set image. Now, it might mix together in some different ways, potentially different convex combinations, or the operation might be a multiplicative mixture instead of an additive mixture. But the resulting image looks fairly distinct from the original image, but it's not completely distorted. Since there's just one branch, this is more computationally efficient than AugMix. And since we're using a diverse mixing set, there's a lot of variety in the augmented images. We're not just relying on compositions of augmentations anymore. Instead, we're getting a lot of our variability from the mixing set. It's worth mentioning that the mixing set is not the original training set. This way, we don't need to worry about the confidence of the labels or anything like that. Since these images don't belong to any class, it's not adjusting the confidence in the image. Let's now turn to the PixMix pseudocode. The augment function at the bottom is fairly simple. It's just a random sampling from different Python imaging library operations. Now for the PixMix function, it's a function of the original image, a mixing picture, and some parameters. At the first step, x of PixMix is randomly chosen to be either an augmented version of the image or the original image. Then we'll mix for a random number of rounds. The mixing image is either an augmented version of the original image or the mixing pick. And the mixing pick is from a mixing set. It could be a set of fractals or natural images or feature visualizations. All those are possible mixing sets. Then we sample a mixing operation, which would either be an additive mixing or a multiplicative mixing. X of PixMix is then the mixing op applied to the X of PixMix image and the mixing image, which is also a function of beta, and beta is basically going to affect the convex combination. That's applied for several rounds, and then the image is outputted. Now let's see how PixMix compares to various other data augmentation techniques with respect to various safety metrics. We can see that PixMix does better than some of the data augmentation techniques discussed in this lecture and previous lectures. For example, on corruptions, the other techniques vary around 50%, albeit Mixup does improve the corruption robustness by a small amount. PixMix improves it by approximately 20 percentage points. PixMix also does better on various other safety metrics, which we'll describe later in this course, such as calibration and anomaly detection. Consequently, some data augmentation techniques can be useful for various safety metrics, and some might just help with some, but have a mixed effect overall. It's also worth mentioning that many of the data augmentation techniques presented in this lecture don't actually improve typical accuracy that much. They might just slightly improve it or not really change it at all. Some of them just improve safety metrics, so it's possible to improve safety without having any impact on the overall capabilities of models in typical vanilla situations.